Okay, so X-ray diffraction, as you all know, has been for the past 100 or so years, has been one of those pioneering technique which has contributed to developing structure property relationships in a variety of systems, all the way from condensed matter physics to chemistry to biology to medicine. X-ray diffraction has played a critical role in developing structure property relationships. Of course, it should be expected that X-ray diffraction will also play a critical role in material characterization. And so operando XRD studies have been developed, and they have provided a lot of information on battery materials and how the structure of battery materials can sort of give rise to properties or functions of these materials in operating batteries. Here is an example of X-ray diffraction. Here is an example of X-ray diffraction where a transmission XRD has been taken, and the conversion of lithium iron phosphate to iron phosphate can be monitored. So nowadays, X-ray diffraction can be done relatively fast at a synchrotron. You can get high quality spectra in sub-second like timescales. So one should be able to understand or study things like dynamics of electrodes during a pulse charge or a pulse discharge, for example. So you can really collect X-ray diffraction at a very fast rate. And so you can follow things that happen in batteries very well. Additionally, X-rays cover a wide range of energies. And with hard X-rays, you can penetrate a lot of matter. So you can actually study full cells and even prismatic cells of the order of 5 ampere hours or 10 ampere hours. You can actually study them. You can study 18650 cells and other bigger cells which are commercially available. While X-ray diffraction has been very successful, the materials that are being considered now are also have a fair amount of complexity. The materials might be of nano material in nature. They might have amorphous regions, or alternatively, they might have dopants or more complex system where the average structure, as you see from X-ray diffraction, might not fully capture the nuanced local structure and its relationship to properties of the material. So in order to do that, one needs probes which looks beyond the average structure. And X-ray absorption methods is another important mode of interaction of light with matter. Broadly, one can say that in the hard X-ray regime, one can classify X-ray absorption based methods into 3 broad categories. There is X-ray absorption spectroscopy, X-ray emission spectroscopy, and X-ray Raman spectroscopy. Of these, X-ray Raman spectroscopy is actually more of a non-resonant inelastic scattering method, but the process could give you information related to core shell spectroscopies. So it's also classified, therefore, under spectroscopy. X-ray Raman is essentially similar to an energy loss spectroscopy that you can perform with X-rays. So it is in some sense analogous to electron energy loss spectroscopy, but using X-rays as the probe photon, or the photons as the probe sort of radiation. So one can combine all the 3 above methods with microbeams and in some cases with nanobeams. And with spectroscopy, you can get elemental, chemical, and structural information at the appropriate spatial length scale. Additionally, you can couple these techniques in well-oriented samples or epitaxially generated samples in either grazing incidence or total reflection geometry, thereby gaining surface or interface sensitivity. So today I will try to go over these three spectroscopic methods. I will initially discuss X-ray absorption spectroscopy and then X-ray emission spectroscopy. If we run out of time, I will not discuss X-ray Raman, but if the time allows, I will go into X-ray Raman spectroscopy. So X-ray absorption spectroscopy is a well-developed technique to perform operando core shell spectroscopy. It is one of the main aspects of X-ray absorption spectroscopy is that it is element specific. So you can look at a specific element in your battery, either it is in the cathode or in the anode or in the electrolyte. And in the hard X-ray regime, a lot of 3D transition metals which are of interest to batteries come in the hard X-ray region. And so you can probe those elements exquisitely with X-ray absorption spectroscopy. Here is an example of LFP, where the lithium iron phosphate is converted to iron phosphate in and studied or monitored operando as the cycling is performed. These can be done by specialized cells that are manufactured to study them during operating conditions. Here is an example of a cell that we commonly use. It's a pouch-like cell, and the stack pressure is then maintained by using a beryllium window. And the beam goes through this beryllium window and the entire pouch as you're performing the X-ray absorption study. With X-ray absorption, you can get information about chemistry a little bit, like the oxidation state. For example, in this case, one can clearly see that this edge region of the X-ray absorption shifts to higher energy, and there are distinct changes in the so-called pre-edge region of the X-ray absorption. The pre-edge region directly monitors the available unoccupied density of states of a particular angular momentum character. In the case of K-edge spectroscopy, you are exciting a 1s electron from the interior of an ion atom into an occupied d orbitals. The d orbitals are the ones which are involved in chemistry in 3D transition metal. And so you can directly probe those unoccupied density of states, either by means of a dipole transition, where the 3D orbitals mix up with p-like orbitals because of symmetry considerations, or through quadrupole transitions, which are not dipole allowed, but are weakly quadrupole allowed. So you can look at those direct transitions of the unoccupied density of states through X-ray absorption spectroscopy. Lastly, you can measure extremely dilute constituents with X-ray absorption spectroscopy. So you can measure things of the order of tens of parts per million if required. And so it's a probe which can give you a lot of information about dopants, which are now quite present in many of the battery materials. So the extended X-ray absorption also provides key information on the local and medium range environment in an element specific manner. So here I'm showing the spectrum of a calcium in an electrolyte. The region which is very close to the edge, which is where the calcium 1s electron is excited, has the pre-edge and the Zanes region. And past it, say like about 20 eV above this threshold, you start seeing these oscillations which have constructive and destructive interference. So these constructive and destructive interference that you're seeing here in the absorption coefficient constitute the extended X-ray absorption region. This region has a lot of information. It's extremely rich in structural information about the central absorbing calcium atom. So as the incident energy is changed and you go past this threshold, the electron, which is kicked out by this 1s absorption, gains kinetic energy. It becomes a free electron in the continuum, and it gains kinetic energy. That is, the excess energy from the X-rays is deposited onto this free electron. As you know that if it has a kinetic energy, associated with it must be a momentum. And it must have this momentum must along with it, because it's a particle as well as a wave in a quantum mechanical approach. You're going to see that these electron waves are going to spread out of the absorber and go out spherically outwards. And as it goes spherically outwards, these waves, the photoelectron waves, are escaping from the central atom. So it experiences the central atom potential. It experiences the core potential of the central atom. As the spherical waves spread out in space, they then can interact with backscattering atoms, and a fraction of this outgoing wave will be reflected back by interacting with the potential of the backscattering atoms. So when the incoming and outgoing waves interfere in the vicinity of the central atom, you can start modulating the X-ray absorption. It is this essential nature of modulating of the X-ray absorption which gives rise to XFs. The identity of the atom that is present here decides how much of these electrons would be backscattered and how much of its phase will get changed. So encoded in this XFs is an ability to determine the distance between the absorber and the backscatterer, the number of neighbors around it, which is often called as the coordination number, and what is the disorder, that is, what is the relative disorder between the absorber and the backscatterer. And this process is essentially taking a nano image in a spherically averaged way for polycrystalline samples or for liquid electrolyte systems such as this. So the kind of scattering that you can expect, as in this example for this calcium, is that you can have this calcium-oxygen interaction or interaction between the calcium and this carbon. So these sort of photoelectron scatterings are called as single scattering processes, and it involves two-body correlations. You can also consider the photoelectron bouncing off more than one atom. For example, it could bounce off the oxygen, go to the carbon, and come back to the calcium. When that happens, you have more than two-body correlations. Essentially, in this case, it's a three-body correlation. And so the XFs encodes all information from both single scattering as multiple scattering. And with appropriate analysis, in many cases, you can invert back these signals and model the local structure to about 6 angstrom from the central atom. So that is the fundamental basis by which XFs is performed. You extract these oscillations. It is converted from energy to a wave vector space, and the XFs exists as a series of sine waves in this wave vector space. One can then Fourier transform this sine waves by established methods and then analyze this data using standard approaches, which has now been well developed to extract structural information. So now, as I told you, that XFs is really good at understanding local structures, and it can provide information where the average structure is quite different than what happens in the local structure. So for example, there is a system which is called as lithium-rich class of active materials, which is quite well studied in literature for the past couple of decades. So in these systems, what happens is two different end members, for example, Li2MnO3, which is a lithium-rich phase, and a regular conventional layered component, which is lithium TM3O2, like lithium cobalt oxide, for example, are intermixed at an atomic scale. Now, if you take these materials and you mix them in an atomic scale, what you find with diffraction is that as the composition is varied, this value X is varied in this, the lattice parameter changes continuously in such a way that it follows Vygot's law. And by Vygot's law, what we mean is that in Vygot's law, the solid solution that is formed between Li2MnO3 and LiTmO2, but the lattice parameter of those solid solutions will depend on the concentration of the transition metal in them. So if you use a composition that is in between, what you would see is that the lattice parameter would be appropriately weighted depending on the lattice parameter of the end phases. So Vygot's law is often found to be a very useful construct to understand properties of materials. It has been used, for example, in semiconductors to understand band gaps and how band gaps will change with doping. Now, while Vygot's law is valid on the average scale, as has been shown by Professor Don's work, it is not clear that mixing these things on an atomic level will actually create a fully disordered solid solution, which will follow Vygot's law. Additionally, when you have ions or atoms are of different ionic sizes, you expect that these atoms will induce local disorder or local distortions around its sides. In order to study that, one needs a local probe to follow it. And so here is the local structure of a system, which is a solid solution of the end members lithium cobalt oxide and lithium Li2MnO3. And immediately, without doing any processing, just looking at the raw data, you can say that from the manganese viewpoint, the manganese in this compound, the Li 0.2, cobalt 0.4, manganese 0.4 O2, looks very similar to Li2MnO3, but it looks very different from lithium cobalt oxide. Likewise, the excess of cobalt in this compound manganese cobalt system is similar to that of lithium cobalt oxide. That is, on a local scale, the manganese excess is similar to Li2MnO3 and the cobalt excess is very similar to lithium cobalt oxide. Now, if the system was a complete true solid solution on the very local scale, which is completely disordered, then you would expect that the local environment of manganese and cobalt will look identical. However, it is clear from just this comparison that that is not the case. You can do a Fourier transform of this data, and you can come up with the same sort of explanation. What you find here in the Fourier transform again is that the Fourier transform of the cobalt excess is similar to that of lithium cobalt oxide, while the Fourier transform of the manganese is similar to that of Li2MnO3. So the excess lithium that we are putting, this lithium 0.2, is predominantly clustering around manganese. Local clustering of manganese-rich and cobalt-rich regions are seen. And so manganese-rich areas are similar to Li2MnO3 and the cobalt-rich regions are similar to lithium cobalt oxide. So on a local scale, this material looks very different than what is expected purely on the basis of a randomly distributed solid solution. Now, similar things can be seen in other systems. For example, here is a system which has manganese and nickel, and you can see that as the value of X increases, that is, you are making it more towards the Li2MnO3 side, the XFs, the manganese XFs, starts looking more like Li2MnO3, and this coordination here, which comes from the manganese metal shell, decreases. So that is the local environment of manganese is therefore looking more like pure Li2MnO3, and the excess lithium is again clustered around the manganese. And you can come to the same conclusion that the nickel, on the other hand, has a full complement of 6 neighbors, and as you change X from 0 to 0.5, the changes that are there on nickel are much smaller than what you see in manganese, again showing that the lithium clustering is predominantly around the manganese. So these are the kind of things that you can understand about the average structure in a very element specific manner, which is harder which you are not very perceptible to in X-ray diffraction. The other point that I had made was that XFs is very sensitive to dilute dopants or impurities, and so it can be a very useful probe to see the effect of Li2 of dopants in systems. And here we are going to show, the example I'm going to show is a study of tin dopants in this complex lithium-rich manganese and nickel-based oxide. So if you look at the area-specific impedance of this material, what you notice is that the area-specific impedance in this region, which is in blue here, or the background is in blue, you see that you have a relatively low area-specific impedance. As you go down to this region, the low voltage region, the impedance rises, and for the undoped sample, the X is equal to 0 sample, the area-specific impedance goes up. But if you add small amounts of tin of the order of 0.01 or 0.02, where X is really small, what you find is that the area-specific impedance drops down. So the blue region, we believe that the area-specific impedance in the blue region is controlled by the layered component of this complex material, while the region here is controlled by the Li2MnO3 activated regions, the regions that are developed from the Li2MnO3 like structures. So if we are able to dope tin into these regions, we have a chance of disrupting or changing the behavior in those regions. So that was the goal of the study. And indeed, what we find is that when you put a small amount of tin dopant, we can significantly reduce the area-specific impedance. Now, while the dopant is put in, and our aim was to make sure that the dopant sits in this lithium-rich regions of Li2MnO3-like regions, we needed to prove that that is the case. Now, if you look at the X-ray diffraction, what you will find is that as the amount of dopant is increased from X is equal to 0.1 to 0.2 to 0.5, the solubility of tin goes down. That is, at a value of X is equal to 0.05, you're starting to see some of the tin come out as this Li2SNO3 phase. And then you can also see that for the samples of the order of 0.01 or 0.02, there is increased microstrain, which you can see here in the XRD data. And as you go down to 0.05, the microstrain again comes down, which means that the behavior that you expect for these dopants the microstrain that is there here is relieved when you start going to a large amount of tin dopant. So consistent with this X-ray data, the TEM also shows that you have these regions which are relatively large which are relatively large, and because of the strain, when you add a small amount of tin, these large sort of grains that you see here are broken down into these smaller regions. So you start getting a significant reduction in the grain size, and the amount of stacking faults increases. Additionally, by TEM, you can also see that the tin dopants that are put tend to go towards the grain boundaries. It is present largely between the grains. So there is a tendency for the tin to be ejected out of these small nanodomains that are created, suggesting that the tin is expelled out, and these nanoregions are trying to purify themselves, and these tin goes to these boundary regions. Now, if you study these tin atoms by X-ray absorption spectroscopy, what you find is that you can clearly show that these dilute tin dopants occupy the manganese type sites in tin doped LMR. So they clearly occupy the sites that we wanted them to occupy. However, the tin manganese distance is significantly increased when compared to the manganese distance. So you can see that in pure Li2MnO3, the manganese distance is around 2.85 angstroms. But when you put tin into manganese type sites in Li2MnO3, the tin manganese distance increases by about 0.1 angstroms. So we believe that this significant increase in distance is one of the reasons as to why the tin allows to strain the Li2, strain the samples and create these small domains, which then end up having good kinetics and lowering the area specific impedance of the material in the lithiated, highly lithiated, activated Li2MnO3 regions. So this is the sort of information that is very uniquely obtainable by XFs. You can clearly understand oxidation states, and you can understand local distortions. It appears like there is a hand put up.
So we'll be addressing the questions at the end of the presentation, and I'll make an announcement. Thank you.
Okay. All right, so the next, I'm going to move on and talk about X-ray emission spectroscopy next. While X-ray absorption spectroscopy monitors the unoccupied density of states, X-ray emission spectroscopy monitors the occupied states. So it's a complementary technique to X-ray absorption, but is also quite powerful in the kind of information that you can get out of it. So what happens in an X-ray emission experiment is that you come in with an X-ray which can excite a 1s electron either to the continuum, that is, give it so much energy that it escapes from the potential of the central atom, or you can move it to an occupied state, an unoccupied state right close to the Fermi level. So this, when you move this electron right close to the Fermi level, it is called as a resonant process. You're moving it, the electron is resonantly excited to a bound unoccupied state. So you can do X-ray emission spectroscopy either in a non-resonant manner or a resonant manner. So when this photon excites this electron, a core hole, that is an absence of an electron, is created in this level, in the 1s level. The system becomes extremely unstable because of the absence of this electron. And in the order of about a femtosecond or a few femtoseconds, the system relaxes back. And the relaxation can take place either by many methods, and among them, the chief among them is these so-called fluorescence emissions. And when you have fluorescence emissions, what happens is that an electron from like a 2p level might fall back and fill up this whole state that you have created here. Or you might have an electron fall from the 3p level into this core state, or you could have an electron that comes from the valence orbitals or the occupied states in the valence region into these holes. So all of these things produce emission spectra, which by using crystal analyzers, one can energy analyze these emissions. So the emission that comes from the 2p level, the 2p level to 1s level, is often called as the K alpha emission. The K alpha emission is typically the strongest emission that you would see for this K series. It probably uses up about 25% of the core hole gets filled up by this K alpha emission. About a slightly smaller, lower intensity, which is magnified here by a factor of 8, you can get these lines which are called as the K beta emission lines, which comes from emission from the 3p to 1s level. Or about 500 times weaker, you can get emissions which come from these valence states. They're called as the valence to core emission, and they give rise to these features which are called K beta 2.5 and K beta double prime. So these features are the valence to core excitation features, and because they come directly from the valence band or the valence orbitals, they are quite sensitive to bonding and to the nature of ligands that are surrounding the manganese. These two other emission lines, the K alpha and K beta, also have some ligand sensitivity, but its major sensitivity is to the spin states of the electrons in the 3D orbitals, and in some cases to oxidation state. So you can do these measurements either using all these different emission lines. You can also do them resonantly or non-resonantly. So there is a whole gamut of experiments which fall under this one broad topic, which is called as X-ray emission spectroscopy. And this is sort of like the setup that you would use for it. Your X-rays will come in, it will hit a sample which is there here. The X-rays from that are emitted by the sample are then analyzed by a crystal analyzer, which is then detected by a detector. These crystal analyzers can give you energy resolutions of the order of 1 eV or lower, and so you can measure these spectra with good fidelity. To just give you an example of how such a measurement can be performed and what do you learn out of it, I will give a good example of one of our recent studies where we tried to learn about the oxidation state and local structure of an earth-abundant cathode material, which used both XAS and XCS. And the material that we studied is this Li1.3 manganese 0.5 iron 0.02O2, or in the notation where we believe in the so-called composite notation, it is 0.7 Li2MnO3 and 0.3 LiFeO2. So the experiment that we performed is what is called as a high energy resolution fluorescence detection, where you take an electron from the 1s level and you put it into a 3D level, for example, when you are at resonance, and monitor the K beta emission that comes here. You can see that the K beta has these two lines. One is called as a K beta 1.3 with high intensity and a satellite line of lower intensity. These two lines come because they come because of an exchange interaction between the 3p and 3D levels. So 3p and 3D levels, the radial part of the wave functions overlap between the 3p and 3d. And so the electrons that are present in the 3p level cannot simultaneously occupy the same orbital along with 3d levels apart as expected from Pauli's exclusion principle. So if you have electrons which will end up having similar spin at those regions where there is a probability of the radial part of the wave functions overlapping, the electrons will like to repel each other and will try to separate themselves out. So this sort of an interaction, which is called as an exchange interaction between the 3p and 3d level, gives rise to the splitting in k beta, which then indirectly gives us sensitivity to the spin that is there in the 3d level. So to sort of show how this happens, before I go there, let me just describe this sample. This sample, just like the previous example that I showed you, actually does not form a completely disordered solid solution, but forms a composite material with Li2MnO3 like character and rock salt LiFeO2 like character. Although the material appears uniform in the sort of micron scale, in the length scale of a few angstrom, the material is actually the material has this inhomogeneity at sort of a nanoscale region. You can see that the Li2MnO3 is again similar to the pristine and the Li2MnO3. The manganese edges are similar, while the iron edges of LiFeO2, which is a cubic LiFeO2, is very similar to the pristine. Now you can take this material and you can perform electrochemistry, and you see that in this region, which is marked by red, you expect the normal electrochemistry, which involves the cations. And then during this region, it is called as the activation, where it is expected that something beyond the cation contributes to charge compensation, and it is normally considered to be oxygen activation. Exactly how this process takes place is something which is being debated and studied in the literature for over 2 decades. Now we're going to follow how these follow from the iron and manganese viewpoint. How does the oxidation state and structure change using XRS and X-ray emission spectroscopy? So if you look at the conventional zenes of iron, you will see that as you charge the material to 4.3 volts and 4.8 volts, there are small changes in the pre-edge, but it turns out that the pre-edges of all these different samples, iron in a 4-valent state, iron in a tetrahedral site, and so on, unfortunately overlap. Furthermore, the iron 4 oxygen bond distance and the iron 3, when the iron occupies a tetrahedral site, and the oxygen bond distance tend to be very close. So assigning oxidation state simply based on X-ray absorption or based on measuring iron oxygen bond distances is a little bit more complicated. So to understand this, we resorted to trying to use spin sensitive X-ray emission. So here what you do, as I explained before, is you take an electron, you put it into this sort of unoccupied density of states, which is available. And then you look for emission that comes from the 3p. By means of a crystal analyzer, you can choose a very small region. You can choose a narrow energy spread of the order of 1 eV and monitor this emission as a function of incident energy as you go through the ion absorption edge. Similarly, you can do the same thing by monitoring the K beta prime emission. Now, schematically, what is it that we are doing? So to understand this, let us look at this. In LiFeOH2, iron is in a 3d5 state, and it's a high spin 3d5. So the 5 electrons at the 3d orbital can be shown schematically to have this 5 upspin electrons. Now, when the incident X-ray comes in and excites these electrons that are there in the 1s state, there is one of two options. One is that you can take an X-ray, which is you can take an electron which is downspin, and you can promote it into this 3D orbital. So you can put it over here or here, and in these two cases, you're looking at a downspin electron from the 1s level, which is put into the 3D orbital. Now, you can also take the situation where you take this upspin and try to put it into this orbitals. But you know that this upspin cannot go here because you cannot have two spins sitting in the same level which are parallel to each other. Pauli's exclusion principle will not allow that. So this transition of taking this upspin and putting it over here is not allowed. Okay, so when this spin is parallel to this spin, the jargon that is used is that it is called as a majority spin. And when it is anti-parallel, the jargon that is used is called as a minority spin. So basically what I'm saying is that for this material, this intermediate state, as this is called, you could have only this, the only allowed transition would have this spin from the K shell opposite to the spins that exist here. And then because of exchange interaction, you can get an emission from that, which would be this K beta 1,3 emission, which is a minority spin allowed transition. The majority spin allowed transition, which should come from the K beta prime feature, is not allowed. So if you monitor the K beta emission and you increase the incident energy, you will see no intensity here from the K beta emission. At around 7113, where the pre-edge appears, you will see no intensity in the K beta prime monitored experiment. However, when you monitor it with the ion K beta 1,3, because this transition is allowed, you would see an emission corresponding to the K beta 1,3. And so you will see this classic doublet structure that is expected for ion 3+ in an octahedral site. Additionally, there is this feature that you see, and it is known by prior studies in transition metal oxides that such features arise from non-local transitions. That is, ion from the ion 4p to 3d. You excite a 1s electron with a mixed non-local ion 3d of the neighboring ion atom. And we will not discuss this transition further, and we'll concentrate on this transition which are local to the ion atom. Now, if you take this and go from an Fe3+ to a 3d4+ state, as happens for an Fe4+, and if you assume a high spin state, what happens in a high spin state is now you have only 4 electrons in the D manifold. There is this empty state that is available. And if you have an empty state that is available, now you can either take this upspin or a downspin, and you can put it into this intermediate states. So the presence of this empty orbital or empty state in the 3D manifold allows the majority spin to be occupied. So in this case, both the K beta 1,3 and the K beta prime will be active. So if you monitor now the K beta prime and you increase the incident energy, you will see intensity around this 711.3.7 region. So this is a fingerprint for the presence of 3d4. And it should be noted that it is well known that a system like SRFeO3 is a highly covalent system, and the ground state is actually 3d4 is a linear combination of 3d4 and 3d5 with a ligand hole. But even when this is the situation, this method gives significant sensitivity to this d4 character. So if you ever oxidize an ion 3+ to 4+, this you will be able to see that by monitoring this K beta prime feature. So in summary, what you can do is you can compare. I show here a comparison of 3D5 and 3D4. And you can see that if you have 3D5, you will have no intensity here in the K beta prime. And in the case of 4 plus, you would see significant intensity here in the case of the K beta prime. Okay, so we will use this as a fingerprint to follow the oxidation state and spin state of iron. So here I show you the pristine compound and compared with LiFeO2, and this shows the classic doublet, and you get this sort of broad peak at about the same position for this iron in a 4-valent state. Now, if you look at the K beta prime, you see that there is no intensity here for the pristine compound. So the pristine compound must be D5 iron 3 plus in an octahedral site. This is also consistent with an expected iron-oxygen bond distance of 1.99 angstrom, and the second shell can be fit to metals present at 2.93 angstrom, which we assign to these edge-shared octahedras. Now, if you charge it to 4.1 volts, you reach here. You see that the doublet nature changes a little bit in the K beta 1,3, and a nice sharp feature starts coming here, which comes from the in the K beta prime. So this clearly shows that you are starting to have iron in a 4 plus state as you go to 4.1 volts, and the bond distance shrinks as should be expected for an oxidized iron. You go to 4.3 volts, this peak increases, and then you can see that this feature also increases, and we believe that you have fully developed an iron-oxygen correlation distance of 1.91, and this represents a 1 electron oxidation of the iron 3 plus to 4 plus, as can be viewed by this increased intensity at 4.3 volt. Now, if you go to 4.8 volts on the other hand, what you find is that the intensity actually falls down in the K beta 1,3, but the intensity increases in the K beta prime. The intensity falls down, but the intensity increases in the K beta 1,3. It is well known that if you have iron in a tetrahedral site, you should expect a significant intensity here because of the absence of a center of inversion symmetry in a tetrahedral site. So we believe that what is happening here is that the iron is getting reduced when you go to 4.8 volts, and some of the iron moves into a tetrahedral site. This can be further verified by analyzing the XFs, where we believe that the average bond distance is consistent with iron being both as iron 3 plus in a tetrahedral site and iron 4 plus in an octahedral site. And additionally, you see that in addition to the edge share octahedra, a new intensity in the Fourier transform shows up, which is consistent with an octahedral tetrahedral interaction, clearly showing that some of the iron is now in a tetrahedral site. So by using this combination of spin selective XANES and X-ray absorption spectroscopy, we can get a holistic view of the electrochemistry of the system. Now, because of the short amount of time that is there, I'm just going to show that the manganese XANES is consistent with Li2MnO3, but when you go to 2 volts, there is a huge reduction of manganese. This is similar to what happens in pure Li2MnO3 systems. That is the manganese reduces on discharge. This is unlike what is usually seen in the nickel and manganese based systems, where oxygen redox is reversible. So we don't see much evidence for reversible oxygen redox, but we see a reduction of manganese similar to pure Li2MnO3 systems. When you look at the iron, what you find is that all the iron comes back to an octahedral site. The pink line now is very similar to the pristine compound. And so the iron is back and is present as iron 3, This is also a very interesting finding because normally people, in most other systems, the iron 3, iron 4 redox will get converted into an iron 2, will get converted into an iron 3, iron 2 redox. That redox is suppressed and the system only goes to an iron 3 plus state. So we believe that we have completely understood the system and we would be using this to design an earth abundant cathode in future work. So I showed you a way of doing this spin selective XFs, but a more complete way of doing is to actually do this 2D plane where you measure as a function of incident energy, you measure the emitted energy and generate this 2D plane. So you go to an incident energy, scan the analyzer crystal, and monitor the intensity for these various emission energies. Then you step the monochromator, go to a different incident energy, and repeat the process. By repeating this, you can get this 2D plane, which is sometimes called as the resonant X-ray emission plane or the resonant inelastic X-ray scattering plane. Okay. Now, in the case of the example that I have shown here is K-beta fluorescence. So when you have a K-beta fluorescence, you have the electron flow falling from a 3p to 1s level, and you're pumping the electron from this 1s level to this conduction band. The difference in energy between this photon in and photon out is deposited as energy into the excitation. And that can be shown here as the energy transfer. So for each pixel here, you have a corresponding pixel here. So it's essentially another way of plotting this data. Now you will see that this energy transfer has energies which are very similar to an excitation from the M edge or a 3p excitation. So this is like saying that you're taking an electron from a 3p level and exciting it to a conduction band. So this is now soft X-ray like information. So this energy transfer in this plays the same role as the incident energy in soft X-ray. And so you're getting soft X-ray like excitations using a photon in, photon out method. So this is a very powerful way of getting a complete understanding of the structure, but you do need a detailed understanding of it. And so you can do these cuts on these things. You can slice it. And one of the slices that is done here and shown here is to monitor the intensity at a given fixed incident energy, monitor the energy transfer. And you can see that this is an image-like spectra obtained at different incident energies corresponding to the pre-H transition. So there's a lot of this spectra has a lot of information that one can mine and try to understand the d electronic levels. The other thing that can be done is an example that comes out of other fields is that you can, by monitoring, measuring X-rays at a very fixed energy, you can overcome to some extent the core hole lifetime broadening. So here is a mercury L3 edge, and you can see that this red line here is what you measure with conventional XANES. But if you monitor emission by looking at this L alpha emission in this case, you will sharpen the features. And this is called as a high resolution fluorescence detection. And this is very powerful because once you increase the resolution beyond what is intrinsic core hole, you might start seeing features which can help you speciate different samples. For example, in the absence of high resolution fluorescence, you cannot differentiate any of these mercury compounds. But with high resolution fluorescence detection, you can say that alpha mercury sulfide and the corresponding cysteine compound have similar speciation, while this Hg cysteine 4 compound has a speciation more similar to beta HGS. So this is very powerful in understanding coordination symmetry and the local structure in these compounds. And it is he used quite a bit in speciation studies. So within emission, the last emission study that I would want to just quickly mention is this ligand sensitivity of valence to core. The valence to core X-ray emission is very sensitive to the surrounding ligand. And as you can see, the chlorine in this case of the zinc chloride, which is measured for various compositions, concentrations, appears at a different place when compared to the zinc oxygen from the solvent. So one can use this to speciate and differentiate between ligands of different types. And this can be actually done non-resonantly, and non-resonantly you can even perform it with lab sources. So that is a big field that is now developing, and there are many places where people are utilizing lab-based non-resonant X-ray emission as a very prominent tool in their research.